guy was number 80 in the world, and he was up a set, and all of a sudden there was all this betting on the other guy, like $7 million bet on the other guy, and the other guy came back and won.
Wow.
Yeah. So, yeah, so they're investigating.
It's kind of like golfers take steroids.
Also magical. Most golfers are old, so they still have to 16.
I was being sarcastic.
Heat transfer, this is kind of a, we're going to take a slight detour from what we discussed last time, and then we're going to get back into that same general area. Heat transfer, 3 ways in which heat energy can be transferred from one location to another. This diagram illustrates all 3 types of heat transfer. One is conduction, which is the actual transfer of heat by molecular collisions from one locality to the next. That would be demonstrated by this, what do you call it, fire iron? Poker. Where the heat transfer is going all along the poker, molecule to molecule. Convection is actual heat transfer by the movement of a heated substance. In this case, we have the air heated and demonstrated by a little smoke here. We actually have the actual movement of the heated substance heating the hands above that location. Or radiation is heat transferred by electromagnetic waves. The whole electromagnetic spectrum, which doesn't necessarily need a medium in between. And so it's the waves transferring the energy to the object by heating the object through radiation. If this diagram is not good enough, I have this diagram. So,
I've heard about this picture from several people.
you've heard about this? I think the first time I showed this, no one knew what this team was or what. I think this is a beach volleyball team, evidently after a victory. They're being irradiated by radiation from above and below, because there's radiation reflected off the sand. Of course, there's conduction directly through the sand into the feet here, because that would be heat. And there's convection of heated air traveling up. So they're getting it from all sides. They're well heated. Doesn't seem to matter on the beach. That was a few years ago. A couple years ago. Conduction. On an atomic scale, it's exchange of kinetic energy between microscopic particles by the collisions themselves. Microscopic particles can be atoms, molecules, or free electrons. Free electrons would be a good way to do it because they're easily movable. Less energetic particles gain energy during collisions with more energetic particles. The rate of conduction depends upon the characteristics of the substance. Right, so basically, you're just transferring energy. One is oscillating more or more energetic. You'll transfer energy to the less energetic, and that will follow through the substance. Metals are, in general, good thermal conductors because they contain lots of free electrons that can move through the metal and transfer energy. Electrons can transport energy from one region to another readily. Poor conductors, on the other hand, do not have these free electrons. That would include asbestos, paper, and gases. Poor thermal conductor. Conduction can only occur if there's a temperature difference between 2 parts of the conducting medium. So, unless if both are oscillating at the same temperature, at the same energy, then there's no reason for thermal conduction to take place. Here's an example. We're heating this pan of water on the stove, and start to oscillate. They transfer some energy, and eventually this transfer takes place all the way through the pot and into the handle, and so you have a pot panhandle. If we're going to quantify conduction, if we have Q as the heat transferred through a substance in the time delta T, the power, or the heat per time that's transferred, is power, energy per time. But if it's a wall of cross-sectional area A, length L, and the temperature difference between one side and the next is hot to cold, then we have a heat transfer given by this. Power, which is energy per time, is equal to Ka delta T over L, or you could say cattle, where K is the thermal conductivity of the material, A is the cross-sectional area, delta T is the change in temperature between one side and the next, and L is the length of the substance that you go through. K is the constant of the material, an intrinsic constant of the material called the thermal conductivity. Here are some thermal conductivities of some common materials and the SI system units in joules per second per meter per degree Celsius. And we can see the thermal conductivities of good metals with free electrons, silver, copper, aluminum, quite high in these units. Thermal conductivity of some other substances that do not have free electrons, a couple magnitudes less, several magnitudes less. And air actually being a gas, where you don't have the proximity of molecules to transfer energy as readily, is a very good insulator. So we've got metals, nonmetals, and gas. Gas being the best insulator in this list. If you had a compound slab between your two temperature differences, say I had one slab that had a thermal conductivity of K1 and a width or length of L1, and I had another slab with thermal conductivity K2 and L2, and a third slab thermal conductivity K3 and L3, and I'm going to transfer energy from hot to cold. I can calculate the power, the energy per time, transmitted through this compound structure as this. The amount of heat per time would be, it's cattle, but I took the K and put it in the denominator because I have three different materials, three intrinsic materials, and each material has a different length and a different conductivity. So instead of having the K up top, we're going to divide by the length divided by conductivity for each material in the denominator. Well, we have a name for the length of the material divided by its thermal conductivity, and that's called the R value for that particular material. So, the power transmitted, the heat per time, is equal to the cross-sectional area times the change in temperature between the ultimate two sides over the summation of the R values for those materials. So R is equal to the length divided by thermal conductivity. In British units, which is often the way you would see it if you went into Home Depot and got the R value for material, that is feet squared, degree Fahrenheit, hours per British thermal units, BTUs. Conversion, BTU is 1,054 joules. A foot squared is 0.0929 meters squared. An hour, of course, is 3,600 seconds. And degree Fahrenheit is 0.556 degrees Celsius. Celsius or Kelvin. So ultimately, if you were to convert a British or an R value in British units, you would make all these conversions. So you multiply by 0.0929 to convert feet squared to meters squared, 556 to convert to Celsius, 37 to convert to seconds, or 1054 to convert to joules. And basically what you do is take your R value in British units and divide it by 5.67. It'll give you your R value in SI units. That's easy to remember, 5.67. Remember that value. Here are some R values for some common material. Fiberglass batting, 6 inches thick, 18.8, 3.5 inches thick. The only thing really changing here is the thickness. 10.9, styrofoam 5, brick 4, insulating glass 1.54. We go down and down. The top materials here are our best insulating materials. And again, you divide these values, these R values, by 5.67 if you want to get SI units. Let's try this example. Here's column 37 in your book. The glass window pane has an area of 3 square meters, a thickness of 0.6 centimeters. The temperature difference between its faces is 25 degrees centigrade. What is the rate of energy transferred by conduction through the window? Well, we're given the area, 3 square meters. The change in temperature between the two faces is 25 degrees. We're told it's glass, and we find the thermal conductivity of glass. And the length is 0.6 centimeters. Putting all those values in, looking back on that previous table, for the thermal conductivity, 0.8 for glass, 3 square meters, 25 degrees centigrade, 0.6 centimeter length, 0.006 meters. This translates to 1 × 10⁴ watts, or 10 kilojoules per second. Energy transfer. Try another one. Styrofoam box has surface area of 0.8 square meters, wall thickness of 2 centimeters. Temperature of the inner surface is 5 degrees, that of the outside is 25 degrees Celsius. And it takes 8 hours for 5 kilograms of ice to melt in the container. Determine the thermal conductivity of styrofoam. Well, one of the key here is that your ice is going to melt. That's going to take a certain amount of energy to melt your ice. And we know from previous class that that would be a phase change from solid to liquid. So we can calculate the energy as being the mass times the latent heat of fusion to figure out how much energy would be required to melt the ice. 5 kilograms, and there's 3.33 × 10⁵ joules per kilogram for the latent heat of fusion. That means we need 1.67 × 10⁶ joules to pass through the styrofoam for this to occur. And we're going to do it in 8 hours. So our time is going to be 8 × 3600 seconds, or 2.88 × 10⁴ seconds. So the power is going to be energy per time, 1.67 × 10⁶ joules, divided by 2.88 × 10⁴ seconds, 57.9 watts or joules per second. So far so good. That's our power that must be transferred through that styrofoam in order for the ice to melt. Not what you really want to happen, but that's what's happening. Let's reverse engineer power equals cattle and solve this for the thermal conductivity of styrofoam. So multiply both sides by L, divide by the area, divide by the change in temperature. We get 57.9 joules per second. The length was 2 centimeters, 0.02 meters. Area was 0.8 square meters, and change in temperature was 25 minus 5, or 20 degrees Celsius. So that gives us a thermal conductivity of 0.0723 joules per second per meter per degree Celsius. If I were to calculate the R value for this material in SI and British units, figure out the SI units first. R value is the length divided by thermal conductivity. This was 2 centimeters, 0.02 meters, divided by 0.0723. Gives us an R value in SI units of 0.290. Then I multiply this by 5.67 to get the R value in British units. 1.89 feet squared degrees Fahrenheit hours per BTU. What do you think? So far, plug and chug equation with thermal conductivity. So far. It doesn't get any worse today.
Today, but later on it will.
Yeah, exactly how far down the road we talking.
Pretest one.
Today is a nice plug and chug day. Wednesday will be a little bit more, less plug and chug.
Our brains are gonna explode when we say
So we'll get the 8x11 note card this time, right? I'm kidding.
Maybe 5 by 7. Let's try this. Let's try this on one more problem. It's 38. A thermal window has an area of 6 square meters, constructed by 2 layers of glass, each 4 millimeters thick, separated from each other by an airspace of 5 millimeters. So we have a double pane window. The inside surface is at 20 degrees centigrade, and the outside is at minus 30. What is the rate of energy transfer by conduction through this window? Well, since we have multiple substances, our power will equal the area times change in temperature, the summation of all the R values, which would be the length divided by thermal conductivities. We weren't given the R values, we're given the lengths, and we'll have to get the thermal conductivities from the table. But in this case, we would have 6 square meters, change in temperature between the inside and outside at 50 degrees Celsius. For the window part of it, we have a length of 4 millimeters divided by the thermal conductivity of glass, 0.8. And then for the air, we have 5 millimeters divided by the thermal conductivity of air, another window pane over here. When I add all that up, I get 1.34 times 10 to the 3 watts joules per second. So 1.34 kilowatts would be our power exchange, which seems pretty high, but that's still about a factor of 10 less than when we had just a single cane. All right. 3 kinds of heat transfer. We just looked at conduction. Let's look at convection. The actual movement of the heated substance. In this case, apart from the pollutants and the smoke is actually hot, so the actual movement of that substance would be convection. 2 kinds of convection. If the movement results from differences in density of the gas and commonly occurring, and that would be natural convection. If you're less dense in one area and more dense in another, and there's some kind of natural flow from into the less dense area, that would be natural convection. When the movement's forced by a fan or a pump, it's called forced convection. convection example. Here's a radiator in a room. The radiator warms the air in the lower part of the room. Heated air is less dense. It rises because it's less dense than the other air. So it rises to the ceiling. The dense and cooler air that was up there tends to fall. And as some air is rising and the other air is falling, it causes a current of air, which would be your convection current. In this case, would that convection be natural or forced?
Natural.
Actually, it would be natural convection after you got out of the radiator. It's due to the natural density difference of the air itself. So it'd be, you have no pumps. So it'd be natural convection. Okay, so you did get from that example. Here's another example of convection. Density of the air decreases and it rises, and eventually warms the object above it. I did this last year, so
I was wondering how that.
I'm rediscovering some of my stuff that I put into this demonstration last year. Yeah, that's your experiment today.
Yes.
Okay. The automobile is cooled by a combination of conduction and forced convection. For instance, the water pump will force water to the interior of the engine, where the water will basically be in contact with the hot parts of the engine. So the engine block will cool off by transferring by conduction heat to the water, and the water will be forced to the radiator, where by conduction it will transfer heat to the radiator itself. The radiator will transfer heat by conduction to the outside air, and the air will carry it away. Convection. So, combination, probably a little bit of radiation going on too. Other applications of convection, the hydrologic cycle, the cycle that is responsible for our weather, where heated air rises, cool air falls, and we have this current of air. The rising air often resulting in the formation of clouds, and the falling air, the dissipation of clouds. Heating and cooling in the oceans, El Nino, La Nina. The particular parts of the ocean that get heated more than other parts, causing a transfer of energy by convection through the ocean. Radiator heat in the room, look at that example. Circulatory system, process by which your body keeps you cool on days like today, by transferring heat through your blood and evaporation. Birds in cold weather have a layer of vessel-free fat and ruffle their feathers, increase air pockets to create low thermal conductivity so that they can actually stay warm. Red tides, nutrient-rich water is stirred up, combined with warm water, which tends to be advantageous for the growth of algae. So red tides would be a complication of convection that occurs in nutrient water into non-nutrient water in spring and fall. Last form of heat transfer, radiation. Does not require any direct physical contact. All objects objects radiate energy continuously in the form of electromagnetic waves due to thermal vibrations of their molecules. Rate of radiation is given by Stefan's law, sometimes called the Stefan-Boltzmann law. In Stefan's law, the electromagnetic power radiated, the energy per time, is proportional to the fourth power of the temperature of the object. And it looks like this. Power, energy per time, equals sigma AE, temperature to the fourth power. You kind of rearrange these. If you had sigma EAT, then it would spell out C. That helps to remember. So you have cattle and you have C. This is called Stefan's law. P is power, joules per second, or watts. Sigma is a universal constant. It's the Stefan-Boltzmann constant, and it's equal to, ironically, 5.67 times 10 to the minus 8. Watts per meter squared per Kelvin to the fourth. So that 5.67 comes up again. This is 5.67 times 10 to the minus 8. Easy to remember. So if I don't give it to you on the test, you should remember that, or else look on the matching page. A is the surface area in meters squared. E is the emissivity of the object. No particular units with emissivity. Emissivity varies from 0 to 1, 1 being a very good object radiating as well as absorbing. But the emissivity is also equal to the absorptivity of the object. So the object is emitting and absorbing with the same value. And T is the temperature, and make sure when you use this formula that all your T's are in Kelvin units. So you have to convert anything in Celsius or Fahrenheit to Kelvin. You want an absolute scale. You don't want any negative numbers going into a power that goes to the fourth power. Convert everything to Kelvin. An ideal absorber is defined as an object that absorbs all the energy incident on it. Hence, it would have an emissivity of 1. This type of object is called a black body. We'll have more about black bodies later on. But basically, a black body would absorb everything into it and also emit everything. An ideal absorber is also an ideal radiator of energy. An ideal reflector, on the other hand, absorbs none of the energy incident on it, reflects it all, hence has emissivity of 0. It kind of would depend on the frequencies that you're dealing with, but if you had a, say if you're dealing in the visible range and you had a nice silvered surface, then it could be an ideal reflector, hence not absorbing the energy. Might have helped with your experiment last week, at least in understanding what went on with your two objects that were radiating. Net radiation energy gained or lost each second by an object depends on how much is radiated by the object minus how much is brought in by the object. So, your net power is how much is radiated by the object, C, at the temperature of the object, to the fourth power, minus C at the temperature of the surroundings, to the fourth power. Because whatever you're putting out, minus whatever happens to be coming in, if there's a temperature difference between the two locations. Power radiated by the object minus power radiated by the surroundings. When an object's in equilibrium with the surroundings, it radiates and absorbs at the same rate. and its temperature will not change. So if they're in equilibrium, then there should be no net power transfer between the object and its surroundings. Yes, true.
They're both using the E value of the object, right?
Yes. Both using the E value of the object because it's both emitting and absorbing. Let's try a problem. A sphere that is to be considered as a perfect black body radiator has a radius of 0.06 meters and is at 200 degrees Celsius in a room where the temperature is 22 degrees Celsius. Calculate the net rate at which the sphere radiates energy. So I have a sphere acting as a black body. Emissivity, not given. Emissivity would be 1, because it is a black body. Ideal absorber and radiator. Radius of 0.06 meters squared. So I'm going to have to calculate the surface area of this sphere, which would be 4 pi r squared. What else will I have to be careful about? The temperature, and we're going to have to convert both temperatures to Kelvin. So the temperature of the body at 200 degrees Celsius and the temperature of the room at 22 degrees Celsius. So here's what I got. Emissivity is 1. Temperature of the body is 200 plus 273.15, 473.15. Temperature of the room is 22 plus 273.15. Stefan Boltzmann constant, 5.67 times 10 minus 8. Area of the sphere, 4 pi r squared, gives me 4.52 times 10 minus 2. So once I'm careful about getting all these values, my net energy radiated per time is the energy that's going out minus the energy that's coming in. 5.67 times 10 minus 8 times surface area, 4.52 times 10 minus 2. Emissivity of 1, 473 to the 4th power minus 295 to the 4th power, 109 watts. Joules per second. Application of radiation. Here's an example of radiation, or application. With radiation of electromagnetic energy, white clothing reflects radiation better. So if radiation were coming in, it tends to reflect it and not absorb it as much, keeping you cool. But you would find that a lot of people in, say, in Middle Eastern areas might even wear black clothing. What might happen here is that black clothing would absorb better and would also emit better. The problem is when it emits, it's not only emitting outward, it's emitting inward. So it would emit towards the body. So what you want to do is have enough airspace between you and the clothing so that you might actually have a hot air near the body rising up, creating a convection current, so you can actually have a cooling convection current coming through the clothing that actually might keep you cool that way. At least in theory, that's how it's supposed to work. Another radiation example. Electromagnetic waves carry energy from the fire to the hands. No physical contact is necessary. Cannot be accounted for by conduction or convection. I think I left this out. Okay. A little bit redundant. Other applications of radiation. Most of the heat radiation we're accustomed to are temperatures in a few hundred degrees Kelvin. Hence, they are radiating in the infrared part of the spectrum. So a lot of waves due to radiation that we're accustomed to in our normal life is in the infrared, which we can't see, but some animals can see that. So some nocturnal animals can see in the infrared, hence they have a better chance of seeing you or other animals at night.
Is that the only difference between visible light and invisible light? Is one we see as light and can feel, the other we do not see but can feel.
Yeah, I suppose that'd be one way to say it. Yeah, we just call it visible because we can see it, right? Yeah, I mean, if we could see all the spectrum, then, well, we can,
Cool.
using instruments, we can see all the spectrum. Infrared sensors are used in defense weapons because lots of weapons involve heat. If you were to take your body temperature, a radiation thermometer would measure the intensity of the infrared radiation coming from the eardrum. Use that intensity to calculate the temperature of the body. The sun transmits energy over a spectrum or over a kind of a skewed spectrum, the peak occurring at the surface temperature of the sun, which is around 6,000 K, which is in the visible, what we call the visible spectrum. But there's also lots of radiation in the infrared and in the ultraviolet as well. Greenhouse example, visible light would be absorbed and re-emitted as infrared radiation. So a lot of the radiation, say from the sun, comes into our atmosphere as high energy visible light or ultraviolet light, gets absorbed by objects and by the gas in the atmosphere, and gets re-radiated at a lower energy, a lower frequency infrared energy, and sometimes because of the atmosphere, well, most of the time because of the atmosphere, that infrared radiation gets trapped within the atmosphere and allows our world to be warm. So basically, the greenhouse effect is a good thing, right? Because life as we know it wouldn't exist. We would not be in a warm, temperate, livable climate if there wasn't such a thing as a greenhouse effect. We just don't want it to go overboard. Here's another application, the Dewar thermos flask, invented by Sir James Copeland Sankowski.
Wait a minute. Is that the same one who has a famous distillery?
I don't know, really.
Yeah, Dewar's whiskey.
That must have been on my mind because it really was invented by Dewar. I must have been a goofy in my mind. So this minimizes heat transfer by conduction, convection, and radiation. So the plan is to minimize all three aspects of heat transfer. For instance, evacuated space, a vacuum between the surfaces, allowing for less conduction, because there's no way to transfer between molecules, and convection. Silvered surfaces minimizes heat transfer by radiation, either in or out. So no heat allowed in, no heat allowed out, vice versa. Just minimize the transfer. Pyrex glass, poor conductor, not allowing conduction transfer. Reduced neck size, again, reducing the amount of transfer by conduction and or convection through the neck itself. Very good design. Keeps your substance either hot or cold. Let's look at another radiation example. Calculate the temperature at which a tungsten filament has an emissivity of 0.25 at a surface area of 2.5 times 10 minus 5 square meters will radiate energy at the rate of 25 watts in a room where the temperature is 22 degrees Celsius. We have a filament, very small surface area, 2.5 times 10 minus 5 square meters. We're given the emissivity, 0.25. Temperature of the room is 22 degrees Celsius. And we're given the rate of energy transfer, 25 watts or 25 joules per second. So we know everything but the temperature of the tungsten filament itself. So if we set up our power equation, power equals C, sigma, area, emissivity, temperature of the fourth minus the temperature of the surroundings to the fourth. And solve this for the temperature of the filament. So we're going to divide both sides by sigma, area, emissivity, and add a T naught to the fourth to both sides. So it looks like this. T to the fourth equals our net power over sigma, area, emissivity plus T naught to the fourth. Take the fourth root of that. Put in our numbers. Power is 25 watts. Sigma 5.67 times 10 minus 8. The area of the filament was 2.5 times 10 minus 5 square meters. Emissivity was 0.25. Kelvin temperature of the room was 295. The Celsius temperature was 22. 295 to the fourth power gives us a temperature of 2,898 Kelvin for the filament. Subtract the 273 from that and get 2,625 degrees Celsius for the filament. All right, so far, just two plug-and-chug type equations. South of the unknown, we have the cattle for the heat of transfer by conduction, and we have the seat, the fourth, for the heat transfer by radiation. The convection is just a principle. With heat transfer comes metabolism. Metabolism is the rate of energy transfer while individuals awake and or resting. For a man, that is 1.2 watts per kilogram, which translates to 2.87 times 10 to the minus 4. I think these are food calories per second per degree kilogram. Woman is 1.1 watts per kilogram. Per day, the average man then would consume about 1,700 calories, food calories. So I guess you'd have to multiply this by about 70 kilograms for the mass of a man, and how many seconds there are in a day. Get 1,700. For the average woman, that'd be about 1,400. Normal daily activity requires about 2,500 calories. Energy per kilogram per time for sleeping would be about 1.1 watts per kilogram. Awake but resting, 1.2. Walking, just about 4 times that, 4.2. Running, another factor of 4 or so, 18 watts per kilogram. That is my lecture for today. problems in chapter 20. We're officially done with this chapter now. So everything is game.
So, are we gonna cover, 21, 22?
Yes, so we're not on schedule for that first test. First test is going to be delayed. We'll have to figure out when that comes. Because set up chapter 21 and 22 to go through. We'll figure out whenever we finish those, we'll have the first test. Let's take a look at try conduction problem. 10 looks pretty good. Before we do 10, let's do 9.
Have to go.
Yes.
Due to technical difficulties beyond my control, all of those, not every single problem is available online. If you want some of the problems that are not, then I can burn a DVD. I'm pretty sure that they're all the DVDs. But the program we use for some reason will not, it cuts off some of the problems. There's just nothing I can do with that.
It cuts off them?
Yes, sir.
Or
It cuts off, sometimes it cuts off the end of the lecture and
Really?
different things. So,
The thing that Damon and I were doing?
right.
Really?
So, I think they're all in the DVDs, and I can get copies of the DVDs to everybody that wants every single problem.
Neat. Just bring the DVDs, right?
Right. But we got some if you don't have them, but
Yeah, but,
that's a lot.
yeah. Well, that's a nice offer. Thanks. Thanks, John. All right, so number 9. Maybe we'll do enough here so that nobody will have to convene. Slab of concrete and an insulating board are in thermal contact with each other. The temperatures of their outer surfaces are 68 and 50 degrees Fahrenheit. Determine the rate of heat transfer in BTUs per feet squared per hour. If the R values are 1.93 and 8.7 feet squared degree Fahrenheit hour per BTU respectively. Normally, power for one surface would be cattle. But if we have multiple surfaces, we're going to divide by K. Or we could write this like this. And so for multiple surfaces, power would equal area change in temperature over the summation of all of our surfaces. And I'll divide by thermal conductivity. Or these values are R values. So in this case, we have change in temperature. Everything's in the British system units. And we want to find the power per area. So rearranging this, we have the power per area is equal to the change in temperature over the summation of the R values. We have 68 degrees Fahrenheit minus 50 degrees Fahrenheit over summation of the R values. R values were 1.93 plus 8.7. Everything in British units. So this will give us 18 divided by 10.63. Gives us 1.69 BTUs per foot squared per hour. problem number 10. A cup of coffee is enclosed on all sides in an insulated cup, 1 centimeter thick, in the shape of a cube, 10 centimeters on the side. Well, that's nice. The temperature of the coffee is 95 degrees Celsius, and the temperature of the surroundings is 21 degrees Celsius. Find the rate of heat loss in joules per second due to conduction if the thermal conductivity of the cup is 2 times 10 to the minus 4 calories per second per centimeter per degree Celsius. We have ourselves a cup that nicely is in the shape of a cube, 10 centimeters on the side. So basically we could say that the area that we're talking about for this cup would be what? Surface area. Well, the thickness would be 1/2 centimeter, so let's put that in. Inside this, thickness is 1/2 centimeter. The area, surface area of our radiating object here, so the temperature of this object is 95 degrees Celsius. So the temperature inside is 95 degrees Celsius, and outside is 21 degrees Celsius. But the area we're talking about is actually the surface area of this cube, which would be what? 600 centimeters squared, correct, because one side would be 100 square centimeters, and we've got 6 sides. Our area is going to be 600 square centimeters. We'll keep it in those units.
Open top or closed top?
It's enclosed on all sides, so not only is it a coffee cup, it's one that you can't drink out of. Enclosed on all sides. Find the rate of heat loss, okay? So power will equal cattle. Thermal conductivity of the cup is 2 times 10 to the minus 4 calories per second per centimeter per degree Celsius. I'm going to keep the units in there because we're dealing with units that I don't normally deal with. Calories per second per centimeter per degree Celsius. Area is 600 square centimeters. Change in temperature is
74 degrees.
74 degrees. Length is 1/2 centimeter. The centimeter is going to cancel out. Alright, degrees Celsius is going to cancel out. But you can get it. So we're going to end up with calories per second. So we have 2 times 10 to the minus 4. 600, 74, 1/2 calories per second. 17.76. If I really was picky, I'd say that my change in temperature was my outside temperature minus my inside temperature would be final minus initial. So it would have been 21 minus 95. So I could even say that this is a negative 74, which would make this a negative 17.76 calories per second. The negative just meaning that I'm losing energy per time from this coffee cup. want the answer in joules per second. So how do I convert that to joules?
4186.
4186. These calories are non-food calories, so it's the smaller conversion. 4.186 joules per calorie. That would give us a negative 74.3 joules per second, or negative 74.3 watts. Good? You know that I'm just going to take problems from these handouts for your first test. So I have to remind you. Take a look at number 11. The child has a temperature of 101 degrees Fahrenheit. For total cross-sectional area is 2 square meters. Find the energy loss each second in watts due to radiation, assuming the emissivity is 1. Assume the room temperature is 70 degrees Fahrenheit. Actually, we have a child with the temperature. So, the temperature of the child is 101 degrees Fahrenheit. Not good. And the temperature of the surrounding room is 70 degrees Fahrenheit. Emissivity of the child is 1, or we're going to assume is 1. Cross-sectional area of the child is 2 meters squared. And I think that's it, right? So, what should I do?
Convert your temperatures to Kelvin.
That's a good idea. Let's convert the temperatures to Kelvin. Let's convert to Celsius first. That's a little bit easier. So, let's see. Temperature in Fahrenheit equals 9/5. Temperature in Celsius equals 32. So, temperature in Celsius is equal to 5/9. Temperature in Fahrenheit minus 32. I guess you could say the temperature in Kelvin.
It's 214 maybe.
All that plus 273.15. So, in this case, the temperature of the child, should I put child up here, equal 5/9 times 101 minus 32 plus 273.15. And what did that come out to? 311.48. 311.5 Kelvin. And the temperature of the room will be 5/9 times 71 minus 32 plus 273.15. I suppose you can have this conversion rate on your card. And that would give me what?
I got 295.
295. So our net power will be the do like this: power radiated minus the power absorbed. So it'll be sigma EA, temperature of the child, to the fourth power minus the temperature of the room, fourth power. Sigma is
5.67 times 10 to the minus 8.
5.67 times 10 minus 8. Very good. Emissivity was 1. Area was 2. Temperature of the child, 3 area 11.5. The fourth power minus temperature of the room, 295 to the fourth power. Put all those in there. At a slightly different temperature for the temperature of the room. This is what I got: 217.4 joules per second, 217 watts for the net power radiated.
What'd you have for the temperature of the room?
I had 294.3. Oh, that's because the room temperature was actually 70. So that makes sense.
Still 294.
That sounds good. What do you think? Have a problem like this on the test? No, no problem. Probably what I'll do is, these problems are easier than my normal test problems, so I probably would have in the problem section of your test probably be 8 problems instead of 6. Would be 2 from each chapter.
So, we can do the formula call on this.
Yes. Formula card. Have a look at number 13. Make sure your copy is mine. That's the one with the 5-gram coin dropped in the building. Problem 13. 5-gram coin is dropped from a 300-meter building. If it reaches a terminal velocity of 45 meters per second, and the rest of the energy is converted to heating the coin, what is the change in temperature of the coin in degrees Celsius? The specific heat of copper is 387 joules per kilogram per degree Celsius. All right, so we're going to drop a coin. Mass is 5 grams. So that'd be 0.005 kilograms. And it's going to be dropped from a 300-meter building, 300-meter tall building. And at some point, it's going to reach a terminal velocity, so that means that the air resistance will offset its gravity, so that it will just keep on falling at constant speed at that moment. And that constant speed would be 45 meters per second. So at some moment, they'll have a velocity, a constant velocity of 45 meters per second. And assume that it'll probably hit the ground at that speed as well. That's still pretty fast. 45 meters per second, multiply it by 2.2, converts that to miles per hour. That would be
99.
about 100 miles per hour, right? 100 miles per hour. So yeah, you don't want to be underneath that coin. Where's the change? Okay, so it hits the ground. We're going to assume that all the energy it had left over would go into heating the coin. How do I calculate the energy it would have left over? What's that say? That would be the energy it has kinetically. And so that, okay.
This is what I was thinking. Determine the time, I guess determine the time it takes to reach 45 meters per second. Would it be the distance? Yeah, see, I was thinking, you would have determine the time it takes to reach 45 meters per second, and also determine the distance it travels to get to that 45 meters per second. Then the distance left divided by 45 meters per second will give you the time that the energy is being transferred into heat.
We can do it easier now.
I was getting a little worried.
Strictly energy conservation. When we start off, we have zero velocity, right? So we have a total energy of mgh. And then eventually, some of that energy goes into kinetic energy, 1/2 mv squared. And that's kinetic energy is maintained all the rest of the way. So the difference between the two is what we have left over. mgh minus 1/2 mv. So the energy we're looking at is going to be,
So you can treat this as an isolated system without.
that's the way it's phrased. It says, we're going to say all the rest of the energy is converted to heat in the coin. So, yeah, because we don't know, it didn't say what energy was being lost to friction or anything else. And so we have to assume that. All right, so this is actually going to equal our Q as well. And this would be 5 grams, 0.005 times G, 9.8 times 300 minus 1/2 times 45.
You forgot. Oh, wait, no, you carried the mass on.
Next one, 9.6375 joules. That should be the heat used to heat up this coin. That heat will equal mc delta T. So delta T will equal the heat divided by the mass divided by the specific heat. So that would be 9.6375 joules divided by the mass of 5 grams, 0.005 kilograms. Specific heat of 397. 387. And what do you get? 4.98 Kelvin. So we're talking about a change in temperature. The then that's fine. So it's 4.98 Kelvin or degrees Celsius, either way you look at it. Because Celsius and Kelvin are the same temperature interval. So about 5 degrees Celsius. Did we do any of these work problems last time? Did we just introduce all that stuff and then the first one? That's all in this whole chapter. Look at number 14. This gas in a container expands at constant pressure of 3 atmospheres. Find the work done in joules by the gas if the initial volume is 5 liters and the final volume is 10 liters. Work in general would be equal to negative integral of the pressure times the change in volume from initial volume to final volume. In this case, the pressure is constant. This would be work on something. So that would be negative pressure times the change in volume if you have constant pressure. The work by something would be the negative of this. So it would be the pressure times the change in volume at constant pressure. So this would be the pressure times the final volume minus the initial volume. Expands at a constant pressure of 3 atmospheres. So we have 3 atmospheres, which I'm going to convert immediately into pascals, newtons per meter squared. What is that conversion?
1.0
Close.
times 10.
1.01. That's good enough. 1.01 out of 3 times 10 to the 5th. 1.01 would be sufficient. That converts into, that's newtons per meter squared per atmosphere. So that would convert atmospheres to the SI system. Over here, we've got final volume of 10 liters minus initial volume of 5 liters. I want to make a conversion of liters to cubic meters. What is that conversion?
Point
Yes,
Yeah,
0.001. 10 to the minus 3. 10 to the minus 3 cubic meters per liter. All right, so there's the main thing is those two conversions. So we're going to have 3 times 1.013 times 5 times 10 to the 5 times 10 to the minus 3. That should give us our answer, which would be 1,515 Newton meters. Or joules. What do you think? Look at the next problem right below that, 15. Gas in a container increases its pressure from 1 atmosphere to 3 atmospheres while keeping its volume constant. Find the work done in joules by the gas, and the volume is 5 liters. initial pressure is 1 atmosphere. Final pressure is 3 atmospheres.
It's 0.
Volume is constant. Wanted to see how far I could go. If the volume is constant, how much work can be done by the gas or on the gas? 0. If you don't change the volume, no work done, either way. Can't do any work unless you change the volume. Take a look at number 20. Determine the work done by 5 moles of an ideal gas that's kept at 100 degrees Celsius and expansion from 1 liter to 5 liters. Work done by 5 moles of a gas that's kept at 100 degrees Celsius and expansion from 1 liter to 5 liters. Something's constant in this problem as well. What is constant?
The weight, the mass, the weight, the temperature is constant.
The temperature is constant. Temperature constant at 100 degrees Celsius, which would be 373 Kelvin. Since the temperature is constant, what kind of expansion would this be?
Negative.
Isothermal. Same thermal.
That's right.
Isothermal. And toward the end of the last lecture, we derived a formula for the work done by a gas and an isothermal expansion. So I'm just going to pull that one up. Work done is nRT, natural log, of the final volume over the initial volume. Work done by the gas. Right. That probably will have to be on some corner of your 6x11 card. Or isothermal thermal expansion.
Your cards keep getting bigger.
Yeah.
Yeah, well,
I think we only had a 3x5.
Wait, what kind of expansion is that?
yeah, the card is expanding at constant temperature. It's an isothermal expansion.
Say half on that.
We'll have a book after a while.
We could just put it on half the board.
Open physics notebook.
Have the class work together. Take home. You might have a take home eventually.
Let me warn you about take-home tests when you get up into higher levels. Avoid them like the plague.
Yeah.
Not my take home test. What do I put in here? What in the problem? What does it tell us?
Well, you know how many moles?
All right. So what's N? 5. Okay, 5 moles. What R should I use? You know, we have two choices. We have either the 8.31 or the 0.0821. In this case,
8.2.
this is tricky. This is tricky because usually you'd use a 0.0821 for if you're dealing with atmospheres and liters. And they gave us the volume in terms of liters, correct? They didn't give us the pressure. but it's a little tricky because the answer is in joules. Or the answer is not in atmosphere liters, it's in joules. So we want to use the 8.31 because the liters are going to cancel out here. Temperature is 373. Natural log. Final volume 5 liters over initial volume 1 liter. So now all of our units are SI units. If I do that, I come up with 24,943 joules. As the work done by the gas. Associated with this problem is the next problem, 21. It says 5 moles of an ideal gas expands isothermally at 100 degrees Celsius to 5 times its initial volume. Find the heat flow into the system. It's basically the same problem, only it's kind of made in a more general way. So what do we know? It's going to be isothermal expansion. And the temperature is 100 degrees Celsius. 373 K. 5 times its initial volume, so B final is 5 times B initial. And since it's going to be isothermal, we might be looking at something like this. If it's isothermal, the change in internal energy is what? 0, because there's no temperature change. As we'll see in chapter 21 on Wednesday, there's a direct relationship between internal energy and temperature. If there's no temperature change, isothermal, then the change in internal energy is 0. By the first law, the change in internal energy should equal the heat added to the system plus the work done on the system. And if this is 0, then that means the heat added to the system will equal the negative work done on the system. On the previous problem, we calculated at 100 degrees Celsius for a gas expanding to 5 times its initial volume. We calculated the work done by that gas was 24,943 joules. The heat added to that system will equal the negative work done on the system, which would be a negative 24,943 joules. Because if the gas does work, then the work done on it will be negative. So negative will be positive, 24,943 will be the heat added to that system in order for it to expand and do work itself. So the same answer is 20. We've got just do one more. This work done on the system
Well, I see how it would work.
is a negative work done by the system. Always going to be work done on the system.
That's the work by, okay, gotcha.
So this is the work done by. Negative. take a look at 28. So the gas expands from A to B as shown in the graph. Calculate the work in joules done by the gas. We have a graph there. This is volume in meters cubed. Here's pressure. In atmospheres. And we have an expansion of gas from point A, point B, like that, from A to B. Now the question is, as this gas expands from A to B, calculate the work done by the gas in joules. How do I calculate the work done by this gas?
I would draw like a little triangle, like go down and then to the right, where you can go to the right and then down. And then, alright, and then as the pressure drops, there is no work. Right, and only in that volume part. So from 2 to 8, that's when we gotta change the volume. So we say the work is equal to, the work by it is equal to the interval of EdV. Or we can just say 2 times 8. And then you have to do the other triangle and then subtract the 2.
Well, that's close. I mean, that's a good answer, and that's the only answer I got. So that's just not there. If I actually went from A to B, if I actually went this way, that's exactly what you'd want to do. Because then the area underneath, as you said, from A down to here would be 0 work, and from here to here would be the area of this rectangle down below. But we're actually going straight from A to B along this path, along this diagonal path. Now, if I actually could calculate the function of that line, then I could integrate, work equals negative pressure as a function of volume, dV, from initial to final. And that probably wouldn't be difficult to do. I'd have to just find the equation of that line, put that in here, and do that. The easiest thing on a PV diagram is just find the total area underneath the function. So the work we're worried about is just this area right here, from any point to any point. And since it's expanding, that'll be the work done by this gas. So I just need to find the area underneath this, which would be the area of this triangle plus the area of the rectangle. So the work will be the area of the triangle plus the area of the rectangle. 1/2 base times the height of the triangle, which would be 6 times 4, plus the area of the rectangle, which would be 6 times 2. So that's going to be 12 plus 12, or 24. My units are going to be atmospheres, meters cubed. Which generally is not good units. So how do I convert that into joules? Which thing do I need to convert?
We need to take a,
What's my factor conversion for that?
1 times 10 to the 5.
1 times 10 to the 5, or 1.01. 3 times 10 to the 5. One would do it. But I'll do this. 24 atmospheres meters cubed times 1.013 times 10 to the 5 Newton meters squared per atmosphere. That will give me 2.43 times 10 to the 6 joules. That's the work done by the gas. Sound good? Quickly look at the problem right below that because it's related. The gas expands as shown on the graph. It actually is the same graph. If the heat taken in during this process is 1.02 times 10 to the 6 joules, and 1 atmosphere equals 1.01 times 10 to the 5 pascals, what is the change in internal energy of the gas? Well, we're told that the heat brought in, we're given that. The heat added to the system is given as 1.02 times 10 to the 6 joules. What is the work done on this system? Yes, the negative of what we just calculated here, because this is work done by the system. So the work done on the system would be a negative 2.43 times 10 to the 6 joule. And by the first law of thermodynamics, the change in internal energy is equal to the heat added to the system plus the work done on the system, whatever you're going to add to that system. In this case, that would be 1.02 times 10 to the 6 minus 2.43 times 10 to the 6 gives us a negative 1.01